Is it possible the learning that your machine learning model is getting from 16 column, it can get the same amount of learning from 2 columns? Yeah, this is possible by the use of dimensionality reduction techniques, and let's see how. Hey guys, my name is Shwankit and this is a real data science channel. So in this channel we talk about more generalistic approach of data science, because come on, if you train a machine learning model, you want your machine learning model to be generalized, right? So why not make our learning the journey of data science also generalized? So we talk about generalistic approach to data science, and today we are going to talk about in detail about PCA and eigenvalues and eigenvectors. It's quite a complex topic, but we'll break down into most easy form as it can be, right? And trust me, by the end of the video you will feel a lot confident talking about eigenvalues, eigenvector, because you will see a practical implication of it. You will see where it is used, what effect does it have, and you will see it relation with both the matrix as well, right? How it is related to matrix and vector, and also how it is related to your actual real world application. We'll see like what effect does it had, right? So we'll see both of those things. So let's just dive directly into a video, and yep, let's see. So how we are planning to move ahead in this video, we'll see some points. We'll see what is the need of dimensional reduction, what is the metric transformation, some formula intuition, some variance intuitions, and then we'll see a demo for PCA. So don't get confused. Eigenvalues, eigenvectors are the fundamentals for PCA, and we'll cover both PCA, eigenvalues and eigenvectors here. I'll make sure that you are not confused with different terms here, but you're understanding the what is the main idea of this particular lecture. Okay. So let's first understand the first topic, right? I hope you can see my screen. So need for dimensionality, right? So assume a scenario, right? So guys, there's a simple case, right? If you guys are a little bit of have a fundamental of machine learning, you will know that. If you don't know that, I'm telling you that, right? So the idea is that as you increase the number of features, right? As you increase the number of features, right? Your complexity of your model increases. Complexity of your model increases, right? It's a simple function. As you increase the model features, complexity of a model increases. Now what is the problem in increasing complexity? There's several problems in increasing complexity. The biggest problem is that your model can overfit. As you increase the model complexity, your model turns to memorizing the pattern instead of generalizing it, right? So you have to have a little control over complexity there. Okay, so the biggest problem is overfitting. The other problem is that once it becomes complex, it's hard to compute. Okay, the other problem that it brings is that it takes time. Your learning will take time. Learning will take time because it's a complex process. The code will become hard. The formula for your machine learning algorithm will become hard, right? How will the formula become hard? So for example, if your machine learning formula is something that is coming out to be ax1 plus bx2 plus c, right? So now when it's taking more time, we are having more features. So x1 and x2 will go up to, let's say, xn, and xn could be 200 as well, right? That is the case. So these are some problems that will have with model complexity. There's some basic problems. There are many other problems that can come with high number of features, right? And a common use case where we see this kind of problem is in case of NLP, right? So just giving a basic understanding, what happens in case of NLP is that you break your words into a piece of columns, right? So for example, if I have a sentence, each word of that sentence will become a column, and if you are observing a multiple data, you are observing count, right, of that particular word, right? So this process is called vectorization, right? So in vectorization process, this is just an example, guys, of where this dimensional reduction or higher having many dimensions will pose some problems. So when you do vectorization, what you do, you create vectors for your word, right? You create vectors for your word. Basically it's like my name is Ram, right? If this is a sentence, if I'll vectorize the sentence, each of these words is becoming a column now, right? And let's say I have like 20-30 sentences like this. So in each sentence I'll observe ki, hey, my has occurred one times, name has occurred one time, is has occurred one time, and Ram has occurred one time, because this was one data points. Let's say I have like 16 data like this, and my name is Ram, Ram is good boy, and my name is Shyam. So you see a count of Shyam, right? So my comes 2 time, Ram comes 2 time, right? So this is how a vectorization process happen, where you store the vectors, store the count of the word. Basically count vector, it's a kind of a data stored like this. And other embedding models are also take inspiration from these kind of models. Now the problem is that more words you have, more features you will have, basically the model complexity will increase a lot, because NLP at the end is a clustering algorithm. It's an algorithm, right? And you have many features there. So that is one that is one use case where you can see that higher complexity, higher number of features, they bring higher number of complexity. Now the solution of this is people sat down and they thought that what if we can achieve lower complexity, with higher number of features. Basically you are having many features but you're still having lower complexity. So how will that be possible? So people thought of, hey, what are these features contributing? These features are giving us some insights, right? Or we can say variance, or we can say pattern, right? So the features, they have some hidden patterns, they have some hidden trends, they have some interdependability and many other things, and a machine learning model is aimed to learn those things, right? So people thought that okay, if this higher number of features are giving some insight, variance, pattern to our data, that our machine learning model is aimed to learn, right? So if it is possible, if it is somehow possible that I can convert the insight, variance and patterns of these 16 features, 16 is just a random example I'm taking. If I can convert the variance that is coming out of the 16 feature, or the insight or pattern that is coming out of those 15 features into less number of features, let's say 3 features, right, into 3 features, my problem would be solved, right? Because now these 3 features are basically having the trend or having the pattern or accompanying for the variance. Accompanying for the variance is the right term, I guess. Accompanying for the variance for all of those 16 features, right? They are somehow doing it. We'll come to at a point how they are doing it. And also the number of features are less, right? So my complexity is decreased and my number of features has also decreased, but my pattern on whatever these features are bringing to my model, that amount of value or that insight value is same, right? So this is the idea that people came up with. And let's do one thing, let's park this thought for once, right? So what have we discussed till now? We have discussed that if I can figure out a way in which my number of features are decreasing, right, but the amount of pattern, the amount of value that they would be same, right, then my problem would be solved. Okay, now let's park this thought, okay, and now discuss on another thing. So there's a big concept of linear algebra in data science, right? And one big example of is that we can represent a data, a table as a matrix, right? This is what we can do. We can represent a data table as a matrix, right? And so for example, if I have a matrix 2 4 1 6, this can also be seen as a table, right? This can also be seen as a table, and it is bringing some pattern, is bringing some data change with it, right? And now this is important to understand. Whenever you have a matrix, right, the idea of a matrix in the field of data science is that it brings transformation with it, right? It brings transformation with it. So basically, if I have a vector, okay, and if I do a matrix transformation on that vector, right, if I apply the matrix to the vector, right, what I will get is I will get a vector that has a different direction and a different magnitude. A vector has a direction and a magnitude, okay? So if I do a matrix transformation, if A is my matrix and B is my vector, so if I do a matrix transformation of my vector, I will get a new vector, right? Ideally I will get a new vector V1, let's say, right, which will be having a different magnitude, which will have a different direction than my B vector. So this basically is a thought of matrix transformation, and the thought is that A matrix has done some transformation on V vector, okay? This is the idea. So yeah, that is basically the idea of linear matrix transformation, that if you have a vector, if you have a matrix and if you have a vector, you can do a matrix transformation on that vector and you will get a vector, right? So Now here comes a different formula. This was my metric transformation formula, that A is a matrix which is then multiplied to a vector, gives me a vector 1 which is a transform vector, right? Now people came up with one more formula. Okay, let's say this kind of transformation happens. Now try to understand this, guys. Let's say this kinds of transformation happened. Okay, so this kind of transformation basically says that a matrix A is doing a transformation on a vector V. A matrix A is doing a transformation on a vector V, which leads to a transformation in which the direction of a vector is same. Direction is same and magnitude of a vector is different. Magnitude of vector is different, right? So here you will see that your direction of vector is same. V vector was here, V vector was here. Just the magnitude of vector is changed, and that changing factor would be lambda, right? So that is an idea, right? That here you are doing a transformation, you are having a different vector. Here you are doing a transformation, only the you can say that direction of a vector is changing, the magnitude of a vector is not the direction of a vector is not changing, the magnitude of a vector is changing, right? And it's changing by the factor of lambda. So this equation became the fundamental for eigenvalues and eigenvector. Lambda here becomes your eigenvalue, and V vector becomes your eigenvector. Now let's understand what does it mean, right? So when you see this, guys, when you see this particular function A vector dot V vector is equals to lambda V vector, see this, a matrix can be looked as a data table, right? A matrix can be looked as a data table, right? So let's say I had a 2 by 1 matrix, I had a 2 by 2 matrix, okay, and I'm multiplying it with a 2 by 1 vector. This will give me a 2 by 1 vector. Okay, this will give me a 2 by 1 vector, and the vector has the same direction. Now same intuition is used in our dimensionality reduction. And the idea for dimensional reduction is that any matrix, right, a 2 by 2 matrix, right, would have a vector which will be its eigenvector, and the logic of that eigenvector would be that any transformation you make over that eigenvector, your vector will not lose its direction. Right? Only the magnitude of the vector would be changed. Right? That is an idea of dimensionality reduction, that any matrix would have an eigenvector, right? And that eigenvector does not change its direction. Here what we are doing is that we consider that direction to be variance or the pattern or the insight of that particular matrix. Yeah, so that is an idea, guys, that the direction change that the eigenvector is holding is basically the variance change that it is holding on the pattern change that it is holding, right? This is the intuition behind the value of eigenvectors and eigenvalues. If you just want to observe this thing, right, so it's hard to observe in 3D, but it's easier to observe when you take some example, right? So if you just take a plain sheet, right, let's say palm of my hand is my plain sheet, and if you stretch it, right, by having any two controlling any two points of it, you will see that there is a point on that particular sheet that is not changing its particular direction or change, right? It's just changing in shape, right? That particular point represent the eigenvectors, eigenvalues of your particular data, right? So same thing is applied in an idea of PCA, is that if you'll see here that we have seen how metric transformation affects, we have seen the formula intuition, we have seen the variance intuition, right? So another intuition you can see, the easy intuition is that, let's say you have a river, okay, and the river is flowing, right? That river is continuously flowing river, and in that river you will see that there are a lot of currents, right? Some currents are going this way, some currents are going that, some currents are going this, some currents are going, there are many small currents, but there is one major current, okay, that is enabling the river to flow in one particular direction, right? That is one major current that is enabling the river to flow in one particular direction. Eigenvector represent that particular direction. That particular current is represented by eigenvector. There are many currents in your particular river, right? But there is one major current, right, that you will observe in your river, and that basically is your eigenvector for that particular river, right? Just a simple analogy to understand how data flow here. Here you can see that data flow, the water flow, right? The water flow, you can assume that water flow to be something like insights, right, of a data, right? So yeah, same thing is applied in the concept of PCA, guys. Same thing is applied in the concept of dimensional reduction, right? So that is an idea that what we do, like in easy terms you can say, is what we do is when we have a data that has 16 dimensions, right? When we have a data that has 16 dimensions, 16 dimension data you cannot visualize. You cannot visualize data above 3 dimensions. So 16 dimensions of data, what you will do is that you will convert those 16 dimensions into 3 dimension or 4 dimension as you want. And those 15 or 3 or 4 dimensions that you're converting, they are called principal components of those particular dimensions, right? So basically, if I have 16 dimensions, I will try to find 3 dimensions. If I have to find 3 principal components, I will try to find 3 dimensions, and they will be prior, right? So first one will be having the most variance, second one will have some variance, third one will have some variance of the data, right? See, understand, the goal of your machine learning model is to cover all the variance of the data, right? So that is what you will do, right? That you will try to find 3 dimensions that covers most of the patterns of your data, and those 3 dimensions will be eigenvectors of that, or you can say principal components of your data, right? So all in all, what you will try to do is you will try to find 3 principal components that can cover most of the variance of your data, right, using the concepts of eigenvalues and eigenvectors, right? So that was the theoretical part of it. Now when you do a coding part of it, there are libraries you can use. I'll just demo how you can use a library. And but what I want you to observe here is what change that it brings, right? What change does this particular PCA concept of PCA brings to your machine learning model? Okay, so let's go to a demo part of it. Things will make more sense when you will see things hands-on. So what I have here is simple machine learning model. I have just imported some initial libraries that we require for machine learning. Then we have imported scalar as well. Then I have imported data for breast cancer, right? And it's like a standard data that is there in sklearn dataset. So there is no worry of how we get the data. It's like the standard data that I've used for this testing purpose. I've done some initial transformation on my data. Because this data had a bit of uneven values. Some values are large, some values are low. In those particular cases, you should do a transformation of your data. So I have done that, and once I have done that, you will see that I have imported sklearn.decomposition import PCA. See how meaningful that word is, decomposition, because you are decomposing your 16 dimension into 3 or 4 dimensions, right? So now I have written components. Okay, I want my data into 2 components. How many data I had here, right? So I had a DECR data, feature name, target name, and target, right? So let's do one thing. Let's just see the dimensions of those data as well, and we divide into 2 components. Then PCA, I did a transformation on the components as well. So now I have components data in XPCA, which is just taking the whole independent variables converted into 2 principal components. Okay, and if I just print this out, so you will see that I have first principal component and second principal component, and you can see a proper difference here, right? So what is the meaning of this, right? To do this, I'll have to do one thing is, I had 30 data in my target data, guys. Okay, 30 data in my scale data. So I had 30 dimensions in my original data frame, and I converted them into 2 dimensions. And this is how they look, right? These are the 2 dimensions that I've converted to. Now if you just see my original data, it looks something like this, right? But you know that there are 30 dimensions to this particular data. Okay, and my total data set is 569. This is a standard data set. You can check this data set out. And then what I've done here, I've done imported train test plate, DC entry classifier I've used, and I've just taken classification report to see how much time does my how well has my model performed. Okay, After that I've just imported time. So time basically why I've used time here, because I want to time my model. I want to see how much time does it take for training for my model with scale data, like the normal data, or the one with 29 dimensions, and I want to see how much time does it take to train the data with 2 dimensions, right? So and what result is have, accuracy wise as well and time wise as well. Okay, so if I run this code, what I've done here, just a train test split, taken the model 1 as decision classifier, I have timed it and model fit and then time again, right? So basically I'm timing the initial and final part, how much timing does it, how much time that my model training took, and then I'm predicting as well. So with my normal data, okay, this one, with my normal data, you will see that I've taken the scale data here, guys. Okay, I've taken the scale data here. You will see that the training time that it took, let me do one thing, let me just run it again, okay, because I was running it, so there might be some values like that. Yeah, so you will see that the training time that this particular model took was 0.007. This was with the scale data that my model took 0.007 seconds. Okay, and my accuracy for training was I mean almost perfect, and for test was, it was something like, you can say 90%. 90% accuracy is not bad, right? Now if I do the same thing with PCA data, that is 2 dimensions, you see my time of the first, notice the time first, okay, the time of my machine learning model went down from 0.007 to 0.001. Now you would be thinking, hey, it's not that much of a big difference. See, this is a simple data set, simple machine learning model. Just observe the change numerically. You have gone from like 0.007 to 1, right? Basically you are doing around 6 by 7% of the change, right? That basically means around 90% of your change of your data, right? So 90% reduction in training time that we have observed with using PCA, right? Now, but reduction in time as well, but let's see what happened to our accuracy. So my accuracy is 0.89. So my initial accuracy was 0.90 and my time was 0.007, right? Now my accuracy is 0.89, basically almost the same, and my time has reduced to 0.001, right? That is reduced by 90%. That is the biggest advantage of PCA, is that you are reducing the number of dimensions, you are holding the value of your data, and because you are holding the value of your data, your dimensional reduction does not lead to any accuracy change, but you reduce the training time a lot. So yeah, that is an advantage of PCA. I'll share some notes for PCA as well along with this video. You can check them out in the comments or in the description of this particular video. And along with that, there's one disadvantage as well, right? So, and I'll tell you the disadvantage fairly, right? So disadvantage is that in my initial data of this breast cancer data, I had some values. For example, let's say some diagnostic value, right? Some diagnostic value was there. So that diagnostic value actually made sense, right? If I show that diagnostic value to a physical practitioner or a doctor, they'll tell me the value of that particular diagnostic value. Hey, see, this particular chemical is high. This means that person has this much of problem in his in his body part or something like that. But when you convert this thing into PCA, now those columns are just named PC1, PC2, right? So there's no business meaning of those columns. That is one advantage that comes with PCA, and that is why techniques of PCA is not everywhere used. But in case of NLP, the one topic that we discussed, it would be a really plus thing, because it reduces your dimensions a lot, it holds a value, and the NLP data is not that complex of a data. The bigger problem is that it's a vast data, right? It's a data that has a lot of number of features. It's a high dimensional data, right? So this technique is highly used there, and if you want to learn the field of generative AI, NLP is a must for you, and to learn NLP, PCA would be a must for you. PCA is a really important concept that is asked in interviews, that is asked in many technical companies, very good companies. They'll ask PCA. If you are stuck with an interviewer who is really good in mathematics, you will be grilled on those topics like PCA, right? So do practice a little bit on the code part, but try to get understanding of theory part, because if you understand theory part completely, if you understand the intuition behind PCA completely, you will feel confident about the coding part, and you will be able to answer the question that, okay, I understand it, right? So yeah, that was all I had for this video. My name is Shubhankit. I work at Worldwide Technology as a machine learning engineer. I also create content over LinkedIn, over YouTube, over Instagram on data science. So you can check out you can check out me on all these platforms, and let me know if you want a video on a specific topic. I also teach data science and grow data skills, right? So yeah, that was all from my side. Thank you.